This video is entitled Concavity and the Second Derivative Test. Well, the first thing we want to talk about here is what exactly is concavity. So the definition here says that if f is differentiable in an open interval I, the graph of f is concave upward if f prime is increasing on the interval, and concave downward if f prime is decreasing on the interval. Notice how I emphasized f prime, not f itself. So basically, concave down has a nature of a shape that curves, opens up in a downward direction, and concave up means the curvature is facing upward. So what they're talking about, the derivative increasing and decreasing. Now you notice this interval, and I have this black line separating the two concavity sections here, but this first one's concave down. Now the function itself is increasing part of the way, then it's decreasing. But that's not what this is saying. Concave downward means f prime is decreasing. So I just kind of drew a few tangent slopes just to kind of give you an idea. Maybe I should have put one at 0 there, but so what's basically happening is that, so if you notice that first tangent slope I have over there to the bottom left right here, that's a positive tangent slope. And then as you move up to the next one, it's still positive, but it's not as steep as the one before, so it's a smaller slope. So the slope's decreasing. That's positive, less positive, 0, a little bit negative, a little bit more negative. So in that interval, the derivative is decreasing, the tangent slopes. Now the next interval, the f prime's increasing because you've got, I'll just make up something. Let's just say -2 slope. And I'll call that one -1. That's increasing to 0. And then slightly positive, slightly more positive. So the slopes are increasing. So therefore we have a concave up interval. Test for concavity. It's going to use a second derivative. If f double prime of x greater than 0 for all x in an interval I, then its graph's concave up on I. If f double prime of x is less than 0 for all x in I, then concave down on I. Now, similar to increasing and decreasing, we're going to make a little sign chart, that sort of thing. We're looking for three things to separate our sign chart. It's where f double prime of x equals 0, and f double prime of x is undefined, yet f of x is defined. You may recall we did that with f prime, and that's where you have those fractional exponents, like x to the 2/3. That's when that will happen. Just like it causes a critical number for the first derivative, it causes a number we're interested in this derivative. Now, they're not called critical numbers in the second derivative, but this is what we want. Those values where the second derivative is 0, undefined, but fx is defined, and discontinuities. Discontinuities always affect the flow of any graph, so they have to be included on whether it's a first derivative or second derivative sign chart. So let's start with this one. We're going to determine the intervals of concavity, and I'm going to use open intervals again, just like I did for the first derivative. So we have h of x equals x to the 5th minus 5x plus 2. We take the derivative. That'll give us 5x4 minus 5. But now we need the second derivative. So take the derivative of that will be 20x cubed. So we want to set that. So we definitely don't have any discontinuities, and we don't have the second derivative being undefined while defined in the first derivative. That will only occur, like I said, with the fractional exponents. So you set this equal to 0, 20x cubed equals 0, therefore we get x equals 0. So that means 0 is the only thing we use on our sign chart to separate our intervals of concavity. So let's see what we have here. Similar to the first derivative stuff, We pick a test value, something less than 0. I pick -1, greater than 0, +1. Look what it says here, sine of the second derivative. So you put this into f double prime. You put, and there it is right here. Remember, we only need plus or minus. We don't have to know anything about the 20s, but -20 means it's negative. The other one, +1, positive. So, and that means the second derivative is negative. Will be concave down in that interval, and then the concave up in the other interval. Now, if you look at the graph, you see that curvature coming along here is a downward facing section, so that's concave down, and then it changes over at 0 and goes to upward. All right. Now, this point where it changes at 0 now has a name. A point of inflection, C, f of c. We may have to, whether or not we have to actually figure out what the y value is, but we would plug our value back into the original function. So now this has to be a point where it exists. So just like the first derivative, we don't, just like discontinuities can't be mins or maxes, discontinuities can't be points of inflection either. So you're looking for these points that we find that aren't discontinuities. And if the graph changes concavity from up to down or down to up, we have what's called a point of inflection, or also known as inflection point. I may use those terms interchangeably. Unlike relative min and relative max, that was two different things, whether it went negative to positive, positive or negative. There's no distinction here. It's called a point of inflection. There's not separate. So minus to plus or plus to minus. So this last example, that would have been a point of inflection at 0, f of 0, and obviously 0 would have been real easy to plug in here. So the point 0, 2 would be your point of inflection, and there it is where I have the dot. Probably have these, I must have this scaled by tens since the 2 is so close down there to make it, especially with that x to the 5th, to make everything fit on there properly. And there's Stewie telling us that point of inflections do not occur at discontinuities, so, and we know that Stewie is never wrong. And this is similar to a definition we had involving that said if you have a relative min or max, then it for sure it came from a critical number. Well, this is saying if you have a point of inflection, then either f double prime of 0 or f double prime of c does not exist at c, but not a discontinuity. Zero f of 0, and remember that was what I was telling you earlier. That's that point which we just saw was 0, 2. All right, let's see what we got here. Yeah, so now I brought in that fractional exponent business here, just to see how. All right, I went sideways with my derivative here, x to the 1/3. Bring that down, makes that 1/3 x to the negative 2/3. Bring the exponent down again. You get negative 2/9 x to the negative 5/3, which, I could drop that x down in the denominator. And that shows you that 0 is undefined at the second derivative. Oh, and I'm also mentioning that 0 is also a critical number. But we're not that concerned with that in this problem. That's more just a reminder. Yeah, that would have been it's a critical number. But then we have this. This is what we're interested in right now, is this part right here. F double prime of 0 is undefined, while f of 0 is 6. F of 0 is a possible point of inflection. And let's 0 this, so let's see what happens here. Now graph this original function x to the 1/3. So 0 f of 0 was not a min or a max, but it is a point of inflection, because you can see it's concave up, and it comes at 0, and it changes to concave down. Now, I'm about 99.9% sure with what I'm about to say here, but not absolute, in case there's some situation I've never encountered or come across in. But you won't have a point that's going to be a min or a max and an inflection point at the same time. That won't happen. So like, it's very possible in this case, like right here, see 0 was a critical number, but it did not produce a min or a max, but yet it yielded a point of inflection. So pretty sure that those mins and maxes and inflections cannot happen at the same point. But you're not going to have any problems where that comes up. But okie dokie, let's see what we got here. This is a pretty easy polynomial. F of x equals negative x to the fourth plus 24x squared. So we jump down here and we have negative 12x squared plus 48. Set that equal to 0. We get x squared equals 4. That gives us two answers. Plus and minus 2. Very important. I've really tried to emphasize that hard on other videos about being careful that you realize that has two solutions, or it kind of messes up the answer big time here, because you would not have one of the proper intervals there. Alrighty, so we separated negative 2 and positive 2. So we have three intervals: negative infinity to negative 2, negative 2 to 2, 2 to infinity. So you see my three test values: negative 4, 0, and 4. And let's see, did I show the value? Okay, here's over here to the right. Obviously, you can do that in a calculator without writing those down, but I could have put them in there. Just be sure that you put your y1 in there as so obviously what I'm graphing here is the original function. So you could have a y1 and a y2 in there. Just be careful what you're testing there. So you see you get negative, positive, negative, like I got right here. Concave down, concave up, concave down. So therefore we have 2 points of inflection. Down to up represents 1. These aren't no discontinuities, so down to up and up to down. And then there we go. So you see there's a concave interval down, and in the middle we got an up section there, and then a down section. Points of inflection are a lot more subtle than mins and maxes. You can see those a lot easier. Like mins and maxes, you see these two maxes right here at the top of those mounds. They're easy to see. But a point of inflection obviously has to be there, because if we're going from concave down to concave up, even though it's more subtle, it's not as visual, it had to change somewhere from down to up, right? It had to go, and same thing here, it had to go from up to down somewhere. But they're not as usually profound on a graph. But you can kind of ballpark where they are for sure. All right, so here's, well, looks like I did the same kind of problem as I did up here, didn't I? Okay, well, that's all right. X to the 2/3. So we have that 0 situation again, because 0 makes the second derivative undefined, while f of 0 is defined. This time I just skipped the part about the critical number. So the only thing that goes in our chart is 0. And we have negative infinity to 0, 0 to infinity. And test values, negative 1 and 1. Now this one, you go to the second derivative. I get negative for both of those. I just kind of that time I put it in manually. I guess I could have done it in a chart there, but still correct. They're both negative. And the graph backs that up. So if you're going from, so it's still considered two separate intervals. Even though they're both down, you still want to treat them as two separate regions. No point of inflection because we didn't change. They're both down. So you didn't change down to up or up to down. Well, look at this picture. See, the graph comes down. First region's down. There's this point of interest here at that 0, and then we have down again. Now, it's kind of interesting because 0 would have been a critical number also from that definition, and kind of this sort of verifies that what I was saying earlier about, so that would have been a relative minimum there at 0. So that other graph I did, it was a point of inflection, but the critical number was not a min or max, and just the opposite here. It's not a point of inflection, but it is a min. Like I said, it won't be both at the same time. Now we'll bring some discontinuities into play here. So right off the bat, you look at this function. X squared minus 9 gives us two discontinuities at plus and minus 3. They must go on our chart because they will separate intervals of concavity. neither plus nor minus 3 can be points of inflection, but they do separate your intervals of concavity, so they must be there. All right, so I'll kind of skip the details on taking the derivative here. Quotient rule, of course. A little messy because we have to do the second derivative. And here's what you would end up. And it gets a little messy on it, but I'll walk through the second derivative a little bit to show you the simplification there. So bottom times the derivative of the top would be negative 18 minus the top, negative 18x, times the derivative of the bottom. Bring down the 2, change that exponent to 1, and then derivative of the inside, which will be 2x, over the bottom squared makes that fourth power. Now in another video, I believe it's probably the chain rule section, when I showed a quotient rule problem where they have a common factor, and I'll just do this real quick again because you might not have needed to watch that video. But there's a quick way you can sort of factor and simplify this, is take the term with the smallest power. So there's x squared minus 9 to the first, to the second, to the fourth. Cancel that one out, and then subtract the other 2 by 1. You can just do that real quick without formally pulling it to the outside, then reducing it. You'll end up with the same thing. So 2 to 1 drops that to 3. Now minus minus here made plus, so you have negative 18 times x squared minus 9 gives you negative 18x squared plus 162. And then here you have 18x times 2 times 2x is 72x squared. And then you have 2 like terms in the numerator you can add together. That makes 54x squared. And the bottom is x squared minus 9 cubed. So you really, because once again, you set a fraction equal to 0. We only care about the numerator. Don't worry about now you need the denominator when you're putting your test values and your derivative, but not setting it equal to 0. So, well, we got sort of cheated here, didn't we? Because when you set this, you solve this, you get x squared equals negative 3, so we get no values. There are no possible inflection points. Now, those values that you set equal to 0, you know, they had, with the first derivative, they have a name. They're called critical numbers, of course. These don't really have a name, so I just call them possible inflection points, and then we see if they actually become inflection points or not. So that's why that's for lack of a better term, I just call them possible inflection points. So let's see what we have here. So now I use the method I used before with the dashed lines to represent discontinuities. So I have negative infinity to negative 3, negative 3 to 3, 3 to infinity. So regardless of the change of concavity, we have no points of inflection because we had no possible inflection points. Test values, and you see over here, plus, minus, plus, plus, minus, plus. So it's concave up, down, and up. But the dashed lines tell me that those are not inflection points. But so that's why it's very important that you don't have to have the dashed line there, but that's why I like to do that for my own benefit. And let's look at our graph, and everything looks good. Concave up, concave down the middle, concave up again. Oh, this is the infamous sad graph here, isn't it? Looks sad. Give it a couple eyes there, and well, kind of sloppy there, but poor sad little graph. All right, that's enough of that nonsense, and we'll move on now. Here's another one with a quotient rule. So it should be very similar to the last one. Well, I hope this one actually produces some critical number. I'm sorry, not critical numbers, possible inflection points. I believe it does. All right, so I'm going to skip the first derivative as far as the process, and we'll start right here. Bottom times the derivative of the top, which will be negative 2x, minus the top times the derivative of the bottom, which will be 2x squared minus 16, times 2x, derivative of the inside, and just like the last problem, I'm taking out the lowest term, first term, 2 subtract 2, go to 1, 4 go to 3. And then I combine the numerator. So you distribute, you have negative 2x cubed plus 32x. This minus turns both of those into plus. So now everything's plus over here. But now we would have 2 times 2x, which is 4x. So I take 4x and multiply it through these parentheses. That's going to give me 4x cubed plus 64x. And this is going to give me x squared minus 16 cubed on the bottom. So we'll set this, you just kind of combine all your like terms. You get 2x cubed plus 96x. Set that equal to 0. Factor out a 2x. Now x squared plus 48 equals 0 will not produce any real solutions because you'll get x squared equals negative 48. But 2x equals 0 does. That produces 0. So now we'll have, our graph will have 2 discontinuities, plus and minus 4, but now we have a value at 0, a possible inflection point. And we'll see if it turns out to be 1 or not. So you see I have the intervals, so I have the dashed lines of discontinuities. So we have 3 points of interest. So it separates it into 4 regions. You see my test values. And then plug them in right over here, and that y2 does represent my second derivative. I probably have y1 in there as my original function for graphing purposes. Yeah, I believe in these new colorful graph ones. The y1 is blue and y2 is red. But I want to graph the red. So look at that. It goes minus, plus, minus, plus. Minus, plus, minus, plus. Down, up, but only 1 point of inflection. Because we cannot include the negative 4 and the 4 because those are discontinuities. Only the 0, f of 0 would be the point of inflection. Not all 3 of those. So always have to pay attention to whether or not they're a discontinuity. And Stewie's reminding us of that fact. Thank you, Stewie. I believe I just changed, this means I changed this problem to an open interval, 0 to 2 pi, not a closed interval. For these kind of problems, I generally like to use an open interval. Intervals of concavity and points of inflection. So let's have a little fun with a trig one here. That's always good. Alrighty, I don't want a trig one to get too out of hand as far as the second derivative getting too nasty or anything, but this one certainly does not get nasty. So, derivative sine, cosine, derivative cosine, negative sine. Derivative of cosine's negative sine. Derivative of negative sine would be negative cosine. And so we set this equal to 0. Negative sine of x equals cos of x, so bring one of them over the other side. Sine of x equals negative cosine of x, so now you're kind of, you don't have to solve an equation for this or anything. Yeah, it would be the same thing as saying tangent equals negative 1, that would be correct. But, you know these are going to be at the pi over 4 values, which is just find out which one. So the fact that sine equals negative cosine means you're looking at the pi over 4s where the square root of 2 over 2 and the negative square root of 2 over 2, that they're opposites, which will be over here at 3 pi over 4. Right? Let's see. Where's my... Yeah, so you see 3 pi over 4 is, they're both opposite. They're the same number, square root of 2 over 2, but they're opposite. And then 7 pi over 4, they're opposite, plus and minus. So 3 pi over 4 and 7 pi over 4 are your possible inflection points. And those are the ones go on my sign chart. This one has no discontinuities or anything. So they would separate them. So I just, this time, I picked some values off the unit circle. There's some problems where I've used decimal radian numbers, but whatever you're comfortable with. So you see I have y double prime here. So the graph is y, so I don't know. I must have graphed that one separately before I put this chart here. That's okay. And so I put in those 3 values, and it goes minus, plus, minus, minus, plus, minus, down, up, down. So both of those then would be points of inflection because they're not discontinuities. Down to up would be 1, up to down would be 1. So we have 2 points of inflection. Look at the graph, concave down. There it's changing right there. So the 0 happened to be the y value for both of those. F of whatever's down, up in the middle, and then kind of, it's hard to tell, but it's definitely down that way. It's curving to the right and below, not up. So concave down. Now we have something called the second derivative test for relative extrema. So we're finding our critical numbers. F prime of c equals 0. But they're saying to exclude the ones where it's undefined. It won't apply to that. And the second derivative of f exists on an open interval containing c. So what we're doing is we're taking our critical numbers and plugging the critical numbers actually into the second derivative without making a sign chart. And it's possible you can determine relative mins and maxes by doing that. So let's see what this says. It says f double prime of c is greater than 0, meaning you're taking the critical number from the first derivative and plugging it into the second. Then f has a relative min at c f of c. If f double prime of c is less than 0, then f has a relative max at c f of c. And if f double prime of c equals 0, the test is inconclusive. Probably means you didn't have a min or a max. Most likely that would be the case. Once again, I can't say 100% of the time, but I would think almost 100% of the time. Maybe there's an exception. Now you might think this seems illogical here, that greater than 0, why would that be a min, and why would less than 0 be a max? Okay, well, let's take a look at that. Let's look at the graph. So you look at this graph, and let's see from what we learn here. I think we know that that's definitely a relative max right there on top, correct? And then a relative min on bottom. But notice that relative max is occurring in a concave down interval. See? In a concave down interval, the second derivative is negative. So that would be correct right here. So it doesn't seem logical, but as soon as you see it explained this way, it makes more sense. So the relative min would always occur in an interval that's concave up. So, interesting. All right, so let's just try that out here. So it's kind of an alternative way to do this instead of the first derivative sign chart. So here's an easy polynomial. We take the first two derivatives, but we're going to take that first derivative to get the critical numbers. Take a look at that. I factored out a negative 4x. Be careful anytime that you factor out a negative sign that you change all the signs accordingly. And x squared minus 3x minus 4 will factor into x minus 4x plus 1. So we end up with three critical numbers, 0, 4, and negative 1. So now you can see at the top right up here, there's the second derivative, which you see clearly I have entered in here as y1, the second derivative. So I put those three critical numbers that came from the first derivative into the second derivative, as you see right here, and also from over here. All right, that means, by definition, the ones that produce the negative, two of them that produce a negative result, so those are relative maxes. So negative 1 f of negative 1 and 4 f of 4 would be maxes. And then because 0 produced positive in the second derivative, it's a min. And sure enough, the graph backs that up. Come up here, there's a max. It dips down just for a second to a min, and then comes up again to a max. Okay, so this is just an interesting idea, relating first, second derivative together. Here's one, I'm just giving you the critical numbers, and I'm giving you the second derivative, so can we apply that test? So real easy in this case. So you're taking those three numbers and plugging it into the second derivative. And I get negative 2, 1, and 5. Negative 2, I get positive. 1, I get negative. 5, I get positive. So the ones that produce positive, the first and the third one, are giving me mins. The middle one that produced a negative is giving me a max. So two relative mins and a relative max. All right, these are always can be interesting for students. It gets next section we'll do another one that's start bringing asymptotes into play here, but these be a little troubling. But what it's expecting you to be able to just to know what the derivatives do. In other words, there's no function here. That's why you have a little bit of margin of error, you know, for what could be the right answer or not in this kind of problem. But I'll show you what I mean here in a second. There's a little bit, but it should have the same general shape. So you just have to know what the derivative's telling you, what the, you know, all this stuff's telling you. So the first thing we have are these three: f of negative 2 equals 0, f of 0 equals 0, f of 4 equals 0. Those are points on the graph. Those are just x and y values. So obviously you need to get those on there. And those get those dots on there. So now the next two things are telling me that f prime of negative 1 equals 0 and f prime of 2 equals 0. That means those are critical numbers. Now they may not be mins or maxes, because remember, you could always have something. Let me go to my scratch page here, because we've seen, like, for example, x cubed is always a classic one to draw here, sort of like that. Oh, well, that's not right. Well, anyway, that's okay. It still angles away. But anyway, that you get a critical number right there where you have a horizontal tangent slope. However, that would not be a min or max. But whether these are min or maxes or not depends on what the rest of the problem says. F prime of x less than 0. So we have to know what that means from the previous section. Three increasing and decreasing functions. That means your graph's decreasing. So your graph's decreasing when x is less than negative 1, but you still read that. You always read this left to right. Don't pay any attention to the way that arrow is pointing. Less than negative 1 means as you're coming from left to right, so it's decreasing. And then notice right below here it says f prime of x is greater than 0 if x is between negative 1 and 2. So that means the graph's increasing. So that guarantees now that f prime negative 1 equaling 0 will be a relative minimum, because now it's going down then up. So in other words, it's not going down and then down again. Then it would just be a critical number that wasn't a min or max. But here's what I was talking about, how you have a little sort of little flexibility. I mean, it's going to come down and turn back around for sure. But notice that it doesn't give you the y value for f of negative 1. So you don't know for sure. So that's what I'm saying. I just drew it right here, but theoretically someone could have drawn it right there and came down and turned around back down there. So that's why you have a little bit of, there's no way to know. But it would still come down because of the properties of the derivative. It would still come down and turn around. So it's increasing, and then you see that f prime of 0 is less than 0 when x is greater than 2. F prime of 2 equals 0. So that means it's going up and then down. Same thing over here on the right side. Is I don't know exactly what the y value is when x equals 2. So who knows? You could have made it go flatter technically, or it could have gone steeper up and then turned around. But anyway, it's going to turn around like that for sure. It's not going to be a sharp point or anything like that. It's going to be a smooth, rounded point. It would be a sharp point if it would have said like f prime, like say right here. Let's look at the first one. If it would have said f prime of negative 1 is undefined and everything else would have stayed the same. But I would have had to told you that f of negative 1 is defined. I would have had to have said that. That just means it would have formed a sharp point. I wouldn't worry too much about that, though. But I just wanted to at least explain that to you. I'm not too concerned about doing that to you. But now you can pretty much get the gist of this graph without even the second derivative information. So you don't actually have to have it, but obviously we should see that it's true. Now I picked a value here, 1/3. I mean, I probably could have, but that was a reasonable choice here. But so this we just said that it's f double prime of 0 greater than 0 and x is less than 1/3. That means concave up. So it's concave up like this. and then f double prime is negative after 1/3. So you see I put the purple dot right about where x equals 1/3, indicating this approximately that's where the point of inflection would be. So it's concave up, then it's concave down. So that just backs up everything we've already done in this section. So I mean this section in this problem, but so you can actually get it done without the second derivative stuff, but the second derivative stuff should match what the graph looks like. So that's the end of this video.